All right, so 5.1, random variables and probability distributions. Here's our goal. To be able to use random variables to quantify random processes and display the data in probability distributions. So we're starting off with our example that we just did, surveying the class, finding out the number of siblings, and the possible outcomes were 0, 1, 2, 3, 4, and 5 or more. I'm just going to fill in what we recorded here. We had 0, only children, which happened every single class period. That is wild. No only children in my class. 6 people had just 1 sibling. 8 people had 2 siblings. 2 people had 3. 1 person had 4. And 2 people had 5 or more. So a random variable is a quantitative variable whose value depends on chance. Because the number of siblings varies from student to student, it is a variable. Suppose now that a student is selected at random. Then the number of siblings of the student obtained is called a
Random variable.
you guys are on it. Random variable. Because its value depends on chance, namely on which student is selected. To represent variables, we can use lowercase letters such as x, y, z. And then to express or represent random variables, we use uppercase, capital, either one. For example, we could use lowercase x to represent the variable number of siblings. So that would be like the value, 0 through 5 and up. But we could use capital letter X to denote the random variable. Number of siblings. More examples of random variables would include the number of students in a class, the number of children in a family, the number of cars entering a car wash in an hour, etc. So why do we use random variables? So as soon as you predict, yeah, that was impressive though. That one wasn't as obvious. Predict outcomes. You can do a bit more math on the outcomes and use more mathematical formulas or processes on the outcomes. And then we have some definitions for probability distribution and probability histograms. You notice in the first lesson of each unit, it lays a lot of the vocabulary foundation. So it does feel like this is probably pretty intuitive and basic. But as you know, as we progress in the unit, it's super important that we have the vocabulary nailed down. So a probability distribution is just a listing of the possible values and corresponding probabilities of a discrete random variable or a formula for the probabilities. And we'll make a probability distribution in just a second based on this frequency distribution. And then a probability histogram, same thing. It's just a histogram, but instead of using relative frequencies on the y-axis, we're using probabilities along the y-axis. So we have here, refer to the sibling example above. Let X denote the number of siblings of a randomly selected student. And determine the probability distribution. So there's 2 parts to this, A and B. Just got to leave room. So we're kind of run out of room. Okay. So we have number of siblings, which is going to be the lowercase letter of X, and we have the probability that our random variable x, see how this is already defined? Let x denote the number of siblings. So when we were talking about probability in Unit 4, we first started off by defining the variable, and same thing here. So the number of siblings, I'm going to scrap 0 since no one had 0. And we'll just jump to 1 sibling, 2, 3, 4, and 5 and up. So then the probability that x equals 1. So how many people had 1 sibling? We've got 6 people with that outcome, right? 6. So out of the total, which is what? 13, 16, 17, 19. So the total here is 19. Couldn't have made 20. Would have been nicer numbers. So have your calculator ready. I'm going to call in people at random. Ready? You're number 1. Jill, you're number 2. 3, 4. You're 4. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I'm going to call on you at random based on a random variable generator, random number generator.
I love that. I'm the last one, I'm 18, then something's wrong.
I got scared. I was 9. I was included in that count.
Okay.
Good thought though.
So that means you are 19.
I'm number 19.
Okay.
Out of the
what if
18 possibilities that will be selected.
Oh, okay. I just say, what if it went
So
down then?
the probability that x equals 1, we're just doing 6 out of 19, and then converting that rounded to 2 decimal places. So I'm going to generate a random number. Be ready. Calculate this. Person number 16. 0.31. Verify person 2. Is that correct?
Yes.
Okay, great.
Wait, I want 31.5.
Yeah, sorry, there is a 5 there, so it is 0.32.
0.32. Okay.
Yeah, but the next one's a 5, so it would around the second one.
Okay, great. And then probability that x equals 2. So what's the fraction that I should write next? Person number 11? Are you 11?
No, 12, so you're 11.
What's the fraction that goes here? For 2, 8. No, that's okay. That's the common mistake. So you don't write the value of the variable, you write the frequency of that outcome, which is 8. So 8 out of 19, and the decimal equivalent to that is person number 14.
That would be 0.421.
So 0.42.
Yes.
Rounding to 2. Thank you. And then probability that x equals 3. What is the ratio there? Person number 13.
It would be 2/19.
2/19 is correct. Nice. And then the fraction, or the decimal, it's rounded to 2 spots. Person number 16. 0.11. Thank you. And then probability that x equals 4. This is a good variety here. Person number 15. 1 out of 19.
It would be 0.05.
0.05, thank you. And the last one, well, we already have that one, don't we? Probability that x is greater than or equal to 5. That looks really sloppy, but that's the greater than or equal to symbol. Probability that x is greater than or equal to 5 is 2 out of 19, so we could just jump up here and say, oh, that was 0.11. So our next task here is to add these all together. So that means I am adding together, summation notation, the probability that x equals any one of those values for the random variable x. So we add these all together. Jill? Well, I'm looking at just these values right here. So the 0.32, and I'm thinking probabilities, they should add up to something close to what?
I think these numbers are
1.
wrong.
So, person number 14.
So, 0.32 plus 0.42 plus 0.11 plus 0.05 plus 0.11 equals 1.01.
1.01. So, super close, and similar to those contingency tables we did last week where you had to add up the whole row, and sometimes it equaled spot on, and sometimes it was a little bit off. Based on our rounding, it can be a little bit off. But that is, it should always be right around 1 when you add those all together. And then the note just says the variable number of siblings is a variable of finite population, so its probabilities are similar to its relative frequencies. And then this is just what we just spoke about on that last question. The sum of the probabilities of a discrete random variable should be 1. And that's the notation for it. Another example, coin tossing. So you're tossing a dime 4 times. All the possible outcomes are listed in this table right here. And it says x is a discrete random variable whose possible values are 0, 1, 2, and 3. Let x denote the total number of heads obtained in 3 tosses. Okay, the variable's been defined for us, just like it was in the previous example. It says use random variable notation to represent the event that exactly 2 heads are tossed. So what that looks like is capital X equals 2. And we use curly braces around that. That's the notation for the event. Set notation. And this says determine the probability that x equals 2. It has to be exactly that number. So how many occurrences of exactly 2 do we have in all the possible outcomes right here? 3, correct. So the probability that x equals 2 is 3 out of 8. Which is, what's the decimal equivalent? 0.375. Cool. 0.375. Thank you. Well, we're going to stick with 2. So let's go 0.38. And then it asks for the probability distribution. Think table, right? So, x is the total number of heads obtained. So we're just going to say number of heads is x. And the probability that capital X equals one of these given values is noted like this, probability capital X equals lowercase x in parentheses. And the possible outcomes are 0, 1, 2, and 3. So the probability that x equals 0 is person number 1. How many outcomes are there where x is 0? Is that you, Sally?
Yeah, we are gonna.
Okay.
0, right?
Well, it's talking about where no heads were flipped in a given outcome.
A 1.
1, good. But just this one here where it's all tails. So 1 out of 8. And 1 out of 8, person number 14. It's random number generators. Got your name.
0.125.
Thanks. 0.125, so we'll go with 0.13. And then the probability that x equals 1. So how many times is exactly 1 heads come up? Person number 1.
Oh my goodness.
What's the probability that there's exactly 1 heads tossed?
So
One head.
there's 3 out of 8. Right?
So this has 3, so that doesn't count. This has 2, but 2. This has exactly 1.
Yeah, so 1.
1,
2 on the bottom.
2, 3. So I thought you said 0 out of 8.
No, I said 3 out of 8.
That was correct. Great.
Yeah.
Only had better hearing. 3 out of 8. Well, that was already calculated above, so we'll just write that in, 0.38. As was the probability that x equals 2, 3/8. Really need to leave more room on here. I'll do that for next time. Sorry about the squishing in of numbers here. And the probability that x equals 3 is number 14.
So x equals 3.
How many times does that occur?
1/8.
1/8, good. Which we already did the calculation for, 0.13. What are the chances? All right, use a random variable notation to represent the event that at most 2 heads are tossed. So that would be x is at most 2. So that'd be less than or equal to 2. Find the probability that x is less than or equal to 2. So that would be the sum of the probabilities. So probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2. So we'll just add those together. Person number 3.
I have not got there yet.
.89, that's correct. Nice job. So .89. Coin tossing. So suppose we repeat this experiment of observing the number of heads x obtained in 3 tosses of a balanced dime a large number of times. Then the proportion of those times in which, say, no heads are obtained, x equals 0, should approximately equal the probability that the event x equals 0. The same statement holds for the other 3 possible values of the random variable x. Use simulation to verify. So just like we did when we did the tossing of the die, we could pull up a simulation and do, say, 1,000 trials. And we would see ultimately, this is an example of a simulation. So this is a simulation or experimental probability. Whereas when we look at these values, like from our table here, where we're basing it off of these possible outcomes, that's just the theoretical probability. We define those at the beginning of Unit 4 as well. So just kind of bringing it back to the forefront, theoretical probability. And that concludes our notes for today.